Hello everyone. From now, we consider the three elements in an AC circuit: resistance, inductor, and capacitors. In all the cases, we use the same expression for current, I equal capital I cosine omega t. Then we will find the expression for the corresponding voltage between the two ends of each element. First element is a resistor. Resistance in the AC circuit. So as I explained, current is expressed I equal I cosine omega t. Then voltage difference between the two ends of the resistance is expressed as I times R resistance. So voltage difference is expressed, substitute, this one is IR cosine omega t. So if you use the phasor diagrams, this is the current of the I, capital I. Then projections onto the horizontal axis is the instantaneous current of the lowercase of the I. For the VR, magnitude of VR, this is IR. The current is in phase with the voltage. Then next element is the inductor in an AC circuit. So current, for the expression for the current exactly same. Then voltage between the two ends of our inductors is expressed L times di dt. I equal I cosine omega t. So V sub L is expressed L times di dt. Then substitute. This expression is here. Minus L I omega sine omega t. Then from the sine functions, we'd like to express this function with the cosine functions, because we'd like to use a phasor diagrams. So this is equal to L I omega cosine omega t plus pi over 2. Phase angles. In this case, this corresponds to the phase angle. In the case of the inductors, phase angle is pi over 2. So this phase angle is a pi over 2. So voltage V sub L leads current I by 90 degrees in the case of the inductors. Inductive reactance is defined by the magnitude of the voltage over current. So from the expression for the voltage, instantaneous voltage is expressed this one. The magnitude can be found I omega L. This is the voltage amplitude. Capital V sub L is equal to the I omega L. So inductive reactance is the ratio between the voltage difference over I. The unit has the same with the resistors, ohm. Then if you substitute this V sub L here, inductive reactance is omega times L. Inductive reactance increases with rapid variation of current. So because of this omega is larger, then inductive reactance increase. Or if you increase inductance of the L, inductive reactance also increases. For a fixed voltage, the current becomes smaller with an increase in inductive reactance. Inductance are used to block high frequency while permitting lower frequency or DC to pass through. Next element is a capacitor in an AC circuit. Again, we use the same expression for the current. Then current and the charge on the capacitor is related. I equal dq over dt. So I, current, is expressed dq over dt. So from this equations, charge on the capacitors is expressed integral I dt. Then you can substitute I equal I cosine omega t. Then this becomes I is a constant moved outside the integrals. Cosine omega t dt. This becomes I over omega sine omega t, 0 to that. So if you substitute the t equals 0, it becomes sine 0 is 0. So it's equals the I over omega sine omega. So we'd like to express this equation with the cosine functions. I over omega cosine omega t minus pi over 2. So this is a phase angles. If you use a phasor diagrams, current is here and the voltage lags I by 90 degrees. This is 90 degrees because of this negative pi over 2. Then we'd like to introduce a capacitive reactance. So we discovered the voltage of a capacitor is expressed in these equations. Amplitude of the voltage is expressed this part. Then we introduce a capacitive reactance is expressed the voltage magnitude over current. You can use this. It becomes 1 over omega c. Again, unit of the capacitive reactance is ohm. Capacitive reactance decreases with rapid variation of current. If you increase the omegas, this omega is increasing, then x sub c becomes smaller. Or increasing capacitance. So if you increase the capital C capacitance, then x sub c is also decreasing. For a fixed voltage, the current becomes smaller with an increase in the capacitive reactance. So capacitors tend to pass high frequency current and block low frequency and DC. Comparison of an AC circuit element. So we consider the capacitor and the inductors. So I is the omega c V sub c. Inductors I current is expressed as V sub L over omega L. So with the increase in the omega, inductor is decreasing following these curves. Capacitors is increasing with the omegas. So loudspeaker uses this characteristic. Inductor and capacitors feed low frequency mainly to woofer, so inductors, and high frequency mainly to the tweeters, so it's capacitors. Okay, next topic is a LRC series circuit. So we consider the 3 elements in the single circuit and all the elements connected in the series. So resistor, inductor, and capacitors. Phasor diagram is very useful. And the horizontal projection on the horizontal axis is the instantaneous current of the lower case of the I. For the voltage, resistor is in phase with the current. This is a resistance, this is a V sub R. For the capacitors, this is a V sub C. For the inductors, actually this is a V sub L. Circuit elements are connected in series. The current at any instant is the same at every point in the circuit. We'd like to find the total voltage in this circuit using the phase diagrams. So as I explained, 3 components, 3 arrows due to the inductor, capacitor, and the resistor are drawn in the same phase diagrams. Inductor voltage leads current by 90 degrees, this phase diagram. And the capacitor voltage lags current 90 degrees. This is capacitors. And the resistor voltage in phase with the current. This is the resistor voltage. Then instantaneous potential difference is the sum of the potential difference, the V sub R, V sub L, V sub C. We could consider this triangle. This quantities is a difference of the V sub L and the V sub C. This is V sub L minus B sub C. So V sub L minus B sub C. And if you consider these triangles, you can apply the Pythagoras theorems. V sub L minus B sub C squares plus B sub R square. Take a square root. This becomes the total voltage of the capital V. Then V sub R is the IR. So V sub L, you can substitute I x L. V sub C is I x sub C. Then you can express the potential difference using these equations. I times square root R square plus parenthesis x sub L minus x sub C squares. So from these equations, we can introduce the impedance. Voltage magnitude is expressed here. Then ratio between the voltage over the current amplitude. V over I is what we call the impedance. Impedance is expressed as take a square root, R square plus X sub L minus X sub C squared. And then you can substitute X sub L equal omega L. X sub C is a 1 over omega C. Then this is the expression for the impedance. For a given amplitude of voltage, resulting current amplitude I will be different at the different frequencies because of the second terms. And the phase angle, this phi, this is phase angle. You could consider this triangle. Phase angle is expressed tangent phi is a V sub L minus B sub C over V sub R. You can substitute, then I is going to be cancelled out. So it becomes omega L minus 1 over omega C over R. So phase angle depend on the frequency of omega. Last topic in this session is a root mean square relation. Relation between the amplitude of voltage and current is expressed this one, V equal IZ. Z is the impedance. And if you divide the square root 2 in the both sides of the equations, left hand side becomes the root mean square value of the voltage. And I over square root 2 becomes I sub root mean squares. If root mean square value are used instead of the amplitude, we obtained very similar equation. B sub RMS equal I sub RMS times Z impedance. Okay, this is the end of the second session.